For the second half of the balloon video, we're going to start playing with the spreadsheet. The way that you can play with the spreadsheet is you go to the web page that is in the link down below. There's a balloon physics Google spreadsheet, and what you can do is you can file download, and you download as a Microsoft Excel. You click on that and it downloads, and then you can open it up in Excel here. And I'm going to try to make this a little bit bigger by going to the 100%, making it like, yeah, hopefully that's a little bit easier to see. All right, now the way that this is done is that these are all the inputs to the program, and then you can basically see how the balloon is ascending and everything in this stuff way down here. All right, so the inputs to this program are the balloon mass, and the balloon mass basically sets the mass of the balloon, obviously, but then it also sets the burst diameter. Kmont makes some balloons, and they tell you exactly what the burst diameter is for given balloon sizes, and I just used 4 of them here. So you can set the balloon diameter, the balloon mass, and it will set the burst diameter automatically. So if I set in a 200 gram balloon, then it sets the burst diameter there. If I set a 600 gram balloon, if I set a 750 gram balloon, then it doesn't know what I'm talking about, and so it sets the balloon burst diameter for 0. But we're going to play with a 1,000 gram balloon because that's sort of the most common balloon that we launch. The payload mass is basically the mass of like all of the parachute and all of the packages that we're going to put on. So it's the sum of everything. I don't think in kilograms, so I put it in terms of pounds, and then I divide by 2.2. So right here it's 10 pounds, but you can change it to like 5 pounds or 1 pound. 1 pound is not very realistic unless all you're doing is launching a tracker, but typically we do lately we've been doing very heavy packages because we put like 4 science payloads and then a couple trackers on, so we usually go 10 or more pounds, so we'll just call it 10 pounds, which is 4.55 kilograms. The tanks of helium, you can change however many you want. It's hard to do less than like quarter separation because it's hard to, when you're out in the field, to figure out like, is this a quarter, is it a third, is it an eighth? So I usually just do like 1 or 1.25 or 2, but 1, usually 1.5 is typically what we do. And then the parachute diameter is when you lay the parachute out completely flat, how big is it? 6 feet is a pretty good parachute diameter. You can find those for like $15-20 online. Then there are all sorts of constants down here which you don't really have to worry too much about unless you want to change like CD of a sphere and CD of a parachute, the mass density of the surface area, the pressure of the surface, the temperature of the surface, newtons to pounds, and the mass of air molecules is given here. Which is 28.9 atomic mass units. So then more stuff down here where basically you say if we change the tanks of helium, say to 1.25, you can see that everything changes down here. So we've started to actually do some math down here. So here we have 1 tank of helium, that is the volume of gas that we have. The pressure in the tank is given. The number of molecules per tank is given. And then the total is basically just the molecules per tank times the number of tanks that we have. And then from that, we had an equation in the last video that tells you the buoyancy from the total tanks of helium, which is like 72 newtons for 1 tank of helium, and that's about 16 pounds. So we could put about 16 pounds on, and it will rise up in the air. That's subtracting off the mass of the balloon. All right, and then gravity is just basically the mass of the balloon plus the mass of the payload multiplied by gravity. That's 54 newtons, or about 12 pounds. So you can see, like, you compare these two numbers, the 72 newtons and the 54 newtons, and the buoyancy is larger than the gravity, so it's going to rise. For the parachute, we're just basically figuring out the parachute area here. So we figured out the parachute circumference divided by 2, and then the radius, and then the parachute area from there. Okay, now the real meat and potatoes of this is that we have altitude here, and we go from 0 to 35 kilometers. That's about the maximum that you would ever really expect to get with a balloon. Typically, you get 28 to 30 kilometers. The temperature of the atmosphere, here I just put in, I just made something up. So 295 is the surface temperature, and then it decreases to about 8 kilometers. It stays constant for about 5 kilometers, and then it starts to increase a bit. So here's the tropopause, and then we're getting into the stratosphere here, and so it's warming up a little bit, and it warms all the way up to 270 degrees by 35 kilometers. I'm not honestly sure how realistic that is, but it's not too bad. H is equal to the scale height, and that was KT over mg. So it's just dependent on the temperature, because m is a constant, g is a constant, k is a constant in this part of the atmosphere. That's true. And then both the pressure and the density just fall off as an exponential. And so if you look here, basically all you're doing is taking this pressure, and then you multiply it by an exponentially decreasing thing. And the exponent goes down as the difference between these two altitudes divided by the scale height. And so it just decreases a little bit between the two altitude levels, which are 0.5 apart. And the exact same thing is true of the pressure and the mass density. And you can see that the equations look pretty much exactly the same, except one is using that, the pressure is using the pressure, and the density is using the density. All right. So then what is this? The balloon volume. I need to make these cells a little bit bigger. The balloon volume was given by the ideal gas law. And so the ideal gas law is PV equals NKT. N is the number of molecules of helium. K is Boltzmann's constant. T is the temperature here. So when we want to calculate the volume, we say that the volume is equal to NKT divided by the pressure. So we look at this, and this is NKT divided by the pressure there. And so you get the pressure in cubic meters. And you can see that the balloon is growing bigger and bigger and bigger. And it gets to be very, very large. So it's 290 cubic meters. And it gets all the way up to almost 1,000 cubic meters. It grows really big because the atmospheric pressure decreases exponentially. So the balloon volume increases exponentially. It's 4/3 pi r cubed. So you solve for r, and you get the balloon radius, which you will see also increases pretty dramatically. Well, I mean, it starts off as about 1 meter for the radius. So it's about 2 meters across to begin with. And then by the end, you're at about 8 meters roughly across. So it's pretty big. The diameter is just 2 times that, which is pretty much exactly what I just said. What happens is that each of these is compared against the burst diameter. So you can see the burst diameter is specified here, which is 7.86 meters. And you go up here, 7.82 meters, hasn't burst, 8.1 meters, it has burst. So the cell color changes from yellow to red, means it's burst. And then on all of these, which is the area of the balloon, I have it conditional. So basically, if this is smaller than the burst diameter, then it actually computes the area. If it isn't, then it just sets it to 0. So it calculates the area of the balloon, basically the area that is going up. So the circle of the balloon. And you can see that that is obviously growing, and it gets up to almost 50 square meters. And then from that, we can calculate from the drag equation, and using all of these, using the density and the area and the drag coefficient and all sorts of other stuff, you can solve for the velocity. And the velocity is like 3.56 meters per second to begin with, and you can see that it actually increases over time. It gets up to about 7 meters per second. All right. Now, what I have found, though, in actual balloon launches is that this actually doesn't necessarily increase. It tends to actually stay pretty steady. Sometimes it increases and then it goes back down to sort of a constant value. Sometimes it stays at a constant value and then it increases and then it goes back down. It sort of goes all over the place. It is definitely true that the velocity typically is between this computed velocity and a constant velocity. And so somewhere in the middle is sort of the truth. And there are all sorts of issues with this because, like, the balloon isn't necessarily a perfect sphere. These equations are just sort of ideal approximations, and the atmosphere is actually doing something sort of different. The temperature is doing things possibly different than what we expect. Who knows exactly? But, it's somewhere between this velocity and this velocity there. Then what we do is we calculate a delta t. So basically this delta t is the time that it takes to go from 0 to 0.5 kilometers. So the distance is 0.5 kilometers. The velocity is 3.56 meters per second. So it takes 2.3 minutes to go from 0 to 0.5 kilometers. Then it takes 2.3 minutes to go from 0.5 to 1.0 kilometers. And you can see as the balloon speeds up, the time actually goes down. So it takes about 1.2 minutes to go from about 25 to 25.5 kilometers. If we hold the velocity constant, then this 2.3 stays exactly the same throughout the entire flight because the velocity is constant. When the balloon bursts, it is no longer ascending. The descending looks very similar. We basically just have a steady state equation with the drag coefficient, or with the drag, and that basically just says the velocity is that the thing is falling at terminal velocity. In actuality, it starts way up here and then it falls downwards, but it doesn't really matter because it's only dependent on the altitude. And so you can see the velocity in meters per second starts off at about 30 meters per second, which is about 100 feet per second, which is really, really fast. And it only takes it about 0.3 minutes to go a half a kilometer. And you can see that it slows down as it's coming down, and it's taking longer and longer and longer to go through those layers, and it ends at about 15.44 feet per second, which is roughly about what a parachute, a person on a parachute hits the ground with. Okay, so then what you can do with that is you can integrate these times, or specifically these times, and you can integrate these times here, and you can get the total time is about 121 minutes for the ascent and about 43 minutes for the descent, for a total time of about 164 minutes. And then I just report those things up here. So the flight time is 164 minutes. The maximum altitude is, I calculate that somewhere over here. So it's basically how high it gets. Oh no, what I do is I report the altitude in feet if the balloon is still ascending. If it's not ascending, then it just gives you a 0. So you just do a max on that, and you come up with the 84,000 feet. You can change these values to give yourself like 3,000 gram balloon, and you can see that the flight time goes to insane values. Why does that happen? Oh, because something happened. Oh, because it doesn't have enough lift to get off the ground. Because the force is not enough, so you have to add more helium. So we need like 1.5 tanks of helium. All right, so then we get up to 108,000 feet there. If we did like 1.25 tanks of helium, then we get up to even higher because the helium doesn't push out the balloon as much. So you can play with this number to say what is the minimum amount of helium. So this is a very slow flight. It's 300 minutes, 5 hours, and it gets up to about 115,000 feet. So this program lets you just play with these numbers. The parachute you can make smaller, like 3 feet, and that you fall very fast then. If you make it 6 feet, then you fall much slower. If you make it like 12 feet, you fall very, very slow. So you can play with all of these numbers and just have fun with your balloon. Download this code or download this Excel spreadsheet and then investigate and see if you can, play around with this and make your balloon fly. And that's, I think, about it. So thank you very much, and good luck.